In today's video I'm going to show you the synthesis of Octasilacubane, or to be more precise, the synthesis of t-Butyl Octasilacubane. The large t-Butyl groups serve to kinetically stabilize the compound. Nevertheless, it is air sensitive, which means the synthesis, cleanup and storage has to be performed in an inert gas. The synthesis starts from the t-Butyltrichlorosilane, which is reduced with sodium. As a catalyst, 12-crown-4 ether is used. And unlike the boring colorless organic cubane, this inorganic cube has a beautiful purple color. This color comes from the delocalized sigma bonds. And it has another fascinating property that I will show you later in the video. This video was supported by Laboratorium Discounter, who provided me with important chemicals for the synthesis. More about them and the discount code that you can use to get 7% off your orders later in the video and in the video description. As already mentioned, this synthesis must be carried out under inert gas. For this purpose, I'm using the so-called Schlenk-Technik. But what does that actually mean?
Schlenk just means that we are working in an oxygen moisture-free environment. And to do that, we're going to use a Schlenk line. And I'm going to explain to you shortly how everything here works. This here is the so-called Schlenk manifold, and it consists of basically two different channels. One channel is for an inert gas, for example argon or nitrogen, and the other one is for vacuum. And you can see here that we have two different valves, and I can open either the valve to the argon line or the valve to the vacuum line, or both, but that wouldn't make any sense. And down here you can see that there are hoses connected, and I can use these hoses to connect them to a so-called Schlenk flask via the valve on the flask. And this way I can evacuate the flask and also let an inert gas flow through to prevent any oxygen or moisture to get in. We will get into detail how everything works when we are actually making the synthesis. What you see here is the setup to provide argon and vacuum to the Schlenk line. This is the hose that comes from the argon cylinder. Here is the argon cylinder, and it has a pressure regulator and a hose which leads to this T-piece right here. And this T-piece splits the argon flow or the argon stream into two different paths. One path leads to the Schlenk manifold, which then can be used. And the other one is basically to release any pressure, because if I just turn on the pressure regulator from the argon cylinder, you will probably blow something up. And this is a washing bottle with a mineral oil inside or silicon oil, which the argon can bubble through if I'm not using it at the Schlenk manifold. And this piece up here is just a one-way valve to prevent oil from flowing back. Right now you can see that the argon is bubbling through the mineral oil because I'm not using it at the Schlenk manifold. And as soon as I open the valve right here, you can see that the argon stopped bubbling through the mineral oil because it is coming out of the hose right here. And if I close it up, you can see that the overpressure is released via this washing bottle. Down here you can see the vacuum pump. It is an ordinary rotary vane vacuum pump, and it is connected via this hose right here to the cold trap. And the cold trap will be immersed in liquid nitrogen, which will be in this dewar down here. And the cold trap basically prevents any solvents and any other stuff from getting into the vacuum pump by freezing it or condensing it inside. And then the cold trap is connected on the other side to the Schlenk manifold to the vacuum line. So first things first, we're going to prepare the whole setup by filling the dewar with liquid nitrogen. We have a 10-liter dewar here, and we're going to use that to refill the dewar during the experiment. Before we immerse the cold trap into the liquid nitrogen, we are going to put a vacuum on the whole system, because otherwise we will condense in air that is currently in the system, which means we have argon in the cold trap. And if we then remove the liquid nitrogen, the argon can expand rapidly and destroy the system and maybe burst some glass. To top the dewar up and to refill it, a second dewar or furnace flask is quite handy, so you won't have to lift the 10-liter door up here and remove the cold trap. Before we use a Schlenk flask, this is a Schlenk tube, we have to bake it out, which means we have to close it up, flush it with argon, and then pull a vacuum on it and heat it to remove any moisture that is absorbed to the glass surface. And that's what we're going to do now. Most Schlenk flasks have these tiny glass hooks here, and they are meant to be used with springs like this one, which holds the glass ground joint on here, and if for any reason there is a overpressure inside the flask, the glass ground joint can lift, release the pressure, and immediately snap back into position to prevent moisture and oxygen to get in. To bake out the Schlenk flask, we are going to connect our tube, which is connected to the Schlenk manifold. And a little tip right here is to color code your hoses at the end, which connects to the flask, and at the end, which connects to the Schlenk manifold. You can see that I have different colors here, because at some point when you're using many flasks and many hoses, you will get confused and open the wrong valve and pull a vacuum on a flask which is meant to be under argon, and maybe pull your solvent into the Schlenk line. So color coding your hoses is a great thing. This is basically the most important educt for the synthesis. It is t-Butyltrichlorosilane, and it was very expensive. I paid almost 200 euros for 10 grams of it. And the last time I did this synthesis, I weighed it in a glove box. I don't have a glove box, so one day before the video I bought together this poor man's glove box right here. But if you don't have a glove box at home, you're not allowed to judge me. And I'm going to use this to weigh in the t-Butyltrichlorosilane, because there's no way to connect it to a Schlenk flask. I thought about 3D printing an adapter with an NS14 ground joint on the other end. The problem is this is not a powder, it is a waxy solid, and there's no way I'm going to be able to transfer it to a flask. So I'm going to flood this thing right here with argon and weigh it in this box. There is a relatively simple synthesis to make this educt. So if you want to see me, or maybe me and Elias, try to attempt to make this, so we don't have to buy it, let me know in the comments.
The gloves were very slippery, too big, and the t-Butyltrichlorosilane is a pretty hard and waxy solid, so it was an absolute joy to wade in.
Alter Schwede, es kann nicht wahr sein hier, ey.
Sehr, sehr gut.
Alter Schwede, ich raste gleich aus. Ich hab sowas von keinen Bock, da jetzt 5 Gramm rauszuholen. Kannst du dir nicht vorstellen.
Ja, was willst du denn machen? Wir brechen das jetzt ab.
After what felt like an eternity, I was able to weigh in 5 grams. And I will now close the flask up and get it out of this absolutely trashy glove box. After getting the round bottom flask out of the glove box, I will definitely connect it to the Schlenk line, pull a vacuum and flood it with argon 3 times, because as you've seen, the glove box, there was definitely oxygen and moisture inside. So I just want to be sure to replace any leftover air in here with argon. Now that we have weighed in our t-Butyltrichlorosilane, we're going to set up our reaction vessel. This is the round bottom flask where the reaction will take place, and we have to boil it under reflux, so we need a condenser on top. To be able to let argon flow through the system from all directions, because if we're opening up here, we need argon from on top here or at the bottom here, and if we're opening up after the reaction here at the condenser, at the neck in the middle, we have to let argon flow in through one of these here. So I'm going to use a NS29 glass ground joint with a valve on top and connect it to the condenser at the top. To later add one of the reagents, we are going to use a dripping funnel. And it's important that this dripping funnel has this pressure equalizer, because if we are going to introduce argon on top here, we need a way for the argon to flow through without the valve being open, so we can flush the system with argon. The last step is to connect all of these openings here to our Schlenk line. Before we can proceed to add all the reagents to our reaction apparatus, we are going to heat it out. So we have a vacuum applied to it right now, and I'm going to heat the entire apparatus, and this way I can drive out the moisture.
Here you can see two mistakes. The valve of the dripping funnel is still closed, which means there is a small amount of air and thus moisture trapped inside. And the second classic mistake, I forgot to add the stir bar. I noticed both mistakes before starting the reaction, fixed them and repeated the bakeout process.
We are first going to dissolve our t-Butyltrichlorosilane in toluene, and we're going to do this with the Schlenk-Technik to prevent any moisture or oxygen to get into contact with either of these two substances. For that, we first have to connect our round bottom flask to a Schlenk line. And now it is very important to Schlenk the hose itself, because there is at this moment air inside. And if we now open the valve at the flask and introduce argon, we are going to flush this air inside the hose into the flask, and we don't want that. So we are going to flush it with argon 3 times by opening the vacuum and then the argon to this hose. So we now have removed all the air inside and replaced it with argon, and we can now open the valve to the flask itself and also open the valve to the second flask with the toluene inside. This hose has been connected all the time, so there is currently argon inside, so there's no need to Schlenk this tube right here. I am now going to use a syringe to transfer the toluene from this flask to this one. And normally these parts would be in an oven at 50 degrees Celsius to also remove moisture, but I don't have a drying oven, so. Another important part is to Schlenk the syringe itself. There is now currently air inside in the cannula itself and also in the airlock on the top here. So we are going to open normally I would do it in a hose, but I don't have another one. I will open the argon line, pull up some argon, get it out, repeat that. And now there's argon in the syringe. I can now open up the flask containing the toluene. And there's argon flowing out of it, so this way there's no way that oxygen and moisture can get inside. To measure a precise amount of the liquid, it is important to remove the argon bubble on top by inverting the syringe, getting it out, and now you can precisely measure the amount you want to transfer, in this case 10 milliliters. And after that, it is important to not pull out the syringe like this, but to add a little bit of argon to have a cushion on top here, so the liquid is not in contact with the air. Now I can open up the second flask where I want to introduce the toluene, and now I'm going to first push out some of the air in the syringe to be sure to remove any oxygen that diffused into the cannula. Get it inside, push out the air bubble, and then get the toluene inside. Before adding the reagents, I want to use this opportunity to thank Laboratorium Discounter for helping me with this video by sponsoring the chemicals, or some of the chemicals. For example, or most notably, the 12 crown 4 ether, which will be used as a catalyst, the toluene and the hexane, which will be used later. Without them, I don't think I would have had the money to do this. And I have a discount code for my viewers. It's Tinkering2023. It will be displayed at the bottom right here. And if you use this code when buying at Laboratorium Discounter, you can get 7% off your order. And the shop has a huge variety of different chemicals. And if you are looking for chemicals, of course for a responsible purpose, you can find them there. You would support my channel by buying there. And all in all, I spent around 700 euros for this experiment alone. So if you want to support me, you can join my Patreon. I would be very thankful for that. Of course, thank you to my current patrons, and thank you to you for watching. Let's keep going. Okay, we can now add 50 milliliters of toluene to our reaction vessel. If the syringe does not have a screw mechanism at the wear lock, always make sure to hold it with your fingers to prevent it from slipping off the syringe and squirting liquid everywhere. Especially when pushing the liquid out of the syringe, it is very important. If you're transferring something pyrophoric like t-Butyl lithium, it is even more important because you really don't want it to spray around in your lab. I can now open the apparatus to the argon, or I did before, and I can now open the side neck here without any moisture or air getting in, because argon is flowing out. While I'm fixing this 12 crown 4 ether here, I want to thank two more persons. The first one is the guy behind the camera, Elias from Elias Experiments, because he filmed or is filming this video and he allowed me to use his place to film this cool experiment, and thank you a lot for that. And I also want to thank the PhD student who made me aware of this experiment in the first place and who let me perform it in the first place in his lab. It was a very cool experiment, and that's why I'm repeating it right here to show it to you. Normally, you would also transfer the 12 crown ether to the round bottom flask, or the flask right here, in a glove box, because, well, there's no way to do this in a Schlenk environment. Sure, you could maybe pull off the cap, put a septum on it, get a cannula, push it through so that argon can flow in, but I don't think it will be necessary. I will be very pissed if that's the reason why the experiment doesn't work. But I'm just going to transfer it with a normal syringe out of this flask it came in. I'm now going to weigh in the sodium, and the problem is I don't have a glove box. So I'm weighing it in the air, but I'm using this inverted funnel here, which is connected to the argon stream to blanket the sodium in the cute beaker here while I'm weighing it in. I can already see all the safety nerds killing me for touching sodium with my fingers. The last step is to add the t-Butyltrichlorosilane, which is dissolved in toluene, to the dropping funnel. Always make sure that the dropping funnel is closed, because of course while baking out the system the dropping funnel has to be open, because there's a tiny amount of air in this glass valve. And now it is important to open this valve here to the argon line, because I'm opening up the dropping funnel, and without this one here open I don't have any argon flowing through the system. And I'm going to use a little bit of toluene to flush out the flask down here.
Here you can see the sodium in the toluene. You can see that it slowly becomes soft. Since toluene with a boiling point of 110 degrees Celsius is above the melting point of sodium at 89 degrees Celsius, the metal ends up as molten drops.
The toluene is now refluxing. If you want, you can admire our absolutely professional setup to cool the condenser. We had to put it on a table because the pump was not able to pump the water this high. And we are now going to start the addition of the t-Butyltrichlorosilane, and we should see a discoloration of the reaction mixture start as soon as we start the addition.
Initially, a reddish-purple discoloration can be seen on the surface of the sodium droplets. With further addition of the t-Butyltrichlorosilane, the surface of the sodium turns dark blue to black. This discoloration progresses until the entire reaction mixture has taken a dark brown to reddish color.
The reaction has now stirred under reflux for 5 hours, and it's time to filter it off. As you can see, we have a black-brown precipitant, which is kind of sparkly. I don't know if you can see it. And we have a reddish-brown liquid layer on the top. The thing now is that we have to filter it off under Schlenk conditions, so without any oxygen getting into it. And for that we're going to use this thing right here. It is basically a filter which can be used with a Schlenk line, and you are going to see how it is being used in a few moments. Normally you would heat this out. I'm not going to heat it out. There are two reasons for that. The first is that it's getting late here. You can see it maybe by the lighting. And the second reason is that we are going to wash it with water, with distilled water anyway, so I'm pretty sure it's not sensitive to moisture, at least not that sensitive. I wouldn't let it stain moisture for a long time. But I know that it is oxygen sensitive. We've let it stand in the lab for a few days and it changed color, so it definitely decomposed. And the reason, and now I'm going to just Schlenk this apparatus, which means I'm going to pull a vacuum on it and flush it with argon 3 times to remove any oxygen, and I'm not going to bake it out. To be able to filter this off, I first have to remove the condenser on top here. So I'm now going to remove the glass ground stopper on the left side here and attach my filtering system. And for that I'm going to remove this end cap right here, and of course I'm going to let argon flow through this part here via the flask and through my dropping funnel to be sure that air is neither getting into my reaction vessel nor into my filtering system. Now that my filtering system is attached and I have another source of argon into my reaction vessel, I can disconnect the dropping funnel. What's quite inconvenient right now is that these valves here are on the side where my liquid will flow into, so I will just try to turn it and avoid the valves. I will now start to wash the product with a mixture of ethanol and hexane in a mixture ratio of 1 to 4. And if you're wondering why there's a spatula inside here, the reason is that I opened it up to scratch around inside a little bit because the frit here was probably too fine and the filtration took forever. And I will now open it up, and if you look at the back here, there is an argon line connected to the frit, so I can, without risking to introduce oxygen, remove the flask. I will nevertheless put a stopper on here, and argon is flowing through the frit. I will use 5 portions of 10 milliliters each. And as you can see, there is a blue product. The ethanol, the hexane is mainly to dilute the ethanol, and the ethanol is meant to decompose any leftover sodium from the reaction. As you can see, we have quite a lot of product in our frit, but mostly it is salt, sodium chloride, which was produced in the reaction. We are now going to wash it with water, 50 milliliters in total, in 10 milliliter portions, and you will see that most of it will be gone, but what is left will have a beautiful color, hopefully. And use the spatula to move everything inside here around. And as you can see on the top here, I think that's our product. Ich glaube, dass unsere Ausbeute gar nicht schlecht ist, du. I will now remove the flask under a slow argon stream to protect it from the environment. And I know there's still some product left in the glass frit, but I think it's a few milligrams and it's not worth trying to get it out of there and risking the main portion of the product. I'm going to use the glass ground stopper that I just weighed, so I can determine the yield later. We finally have our product in our round bottom flask. It is beautiful, even though it's not recrystallized yet. It will be even better when it's recrystallized and you can see the big crystals. And we are going to weigh it now to determine our yield. Beforehand, we weighed the glass ground stopper and the round bottom flask, so we can subtract it from our total weight. And if we do that, we get the weight of our product, which is 0.47 grams, so 470 milligrams, which is really good. I think it is approximately the yield of the paper, and it is also the yield I had when I did this experiment the last time. And yeah, I think that's a great success. I'm pretty tired now, Elias too, so I'm really happy that it worked. Okay, it is the next day now. Elias and I had a good night rest, but we are still pretty tired. We worked for over 16 hours yesterday, I think. And here you can see the product. I already showed it to you yesterday. And now I want to show you a pretty cool property of this compound. But for that, we first have to fill this dewar with liquid nitrogen. And before we continue, we will close the blinds so you can see the effect better. Just for your information, this is a UV light here, which is necessary for the demonstration. As you can see, at room temperature there is no fluorescence visible. So let's lower the flask into liquid nitrogen and see what happens.
As the Octasilacubane cools down, a fluorescence can be seen emanating from the edges as they cool down most rapidly to minus 169 degrees Celsius. This glow slowly spreads to the center until the whole product fluoresces at a wavelength of about 740 nanometers.
Oh, and by the way, we've let the Schlenk-Frit sit overnight with the product inside, and in my opinion it changed color compared to the product under argon, but not that much, so it may be possible to just filter it off under normal conditions and not use a Schlenk filtration setup, but no guarantee on that. I know that it will decompose on air after a few days, but it seems to be stable enough to maybe filter it off just on the air.
For recrystallization, the product was transferred to a 500 ml Schlenk flask, which was baked out before, and 500 ml of dry toluene was added. After installing a reflux condenser, the solvent was heated to boiling to dissolve the Octasilacubane. The magnetic stirrer was then turned off and the temperature of the heating mantle was lowered to 40 degrees Celsius. After 12 hours, beautiful crystals have formed on the walls of the flask. While argon was flowing through the flask, the solvent was removed with a syringe and the crystals were dried in vacuum. They were then transferred to a smaller 100 ml Schlenk flask for storage. To obtain the remaining small crystals as well, the 500 ml flask was washed out with hexane and the suspension was poured into the small flask. The remaining solvent was again removed with a syringe and the crystals were dried in vacuum. The result are beautiful purple crystals that sparkle in the incident light. Here you can see them under a cheap USB microscope. I will use the product to reduce it to a stable radical anion. If you don't want to miss this video, consider subscribing to my channel. Thank you a lot for watching.